Hello again. In this video, we're going to talk about differentials. In fact, we're going to talk about what is known as the differential change in x, labeled dx, and also the differential change in y, which is labeled as dy. And we're going to do this using the linearization process that we talked about in the previous videos. Okay, so let me show you how we come up with dx and dy. Okay, so let's suppose you have a nonlinear function, f of x, which looks like this. And let's suppose you pick some point on that function called x. Now notice at this point x, the y value that comes out would be right here. Now what we're going to do is we're going to change to a different x value. And as we do this, we're going to look at the change in the y value that occurs on the function. Okay, so let's suppose we change to this x value over here, and the amount that we change by is going to be called delta x. So that's going to put us at this point over here, which is going to be x plus delta x. Now, here's where we're going to define the differential change in x, labeled dx. The differential change in x, dx, is actually equal to delta x. So they're the same thing. Okay, so dx is equal to delta x. That's the definition of differential change in x. So another way of labeling this point over here would be x plus dx. You could also call it x plus delta x, since delta x is equal to dx. Now, the more important point to make here is, as we make this change in x here, notice that the change in the y value that occurs on the function would be the distance between y value here and the y value here. Okay, so that distance there is called delta y, right? The change in the y value that occurs when we make this change in the x value down here. Now, having said that, let's also look at the change in the y value that occurs on the tangent line as we make this change in the x value down here. So notice that, again, when you're at this x value here, the y value that comes out would be right here. And then when we change to this x value over here, the y value that comes out on the tangent line would be right here. So the change in the y value on the tangent line would be the distance between those two y values. And that is known as the differential change in y, labeled dy. Okay, so the larger point that you need to sort of see in this diagram is that as we make this change in x down here, called delta x or dx, since those are the same, there's a corresponding change in the y value on the function, which is called delta y. There's also a corresponding change that occurs on this tangent line. That's different. It's called differential change in y, labeled dy. So notice that delta x and dx are the same, but delta y and dy are not necessarily the same. Okay, and so maybe a formula for delta y, you can see delta y would be the y value here, which is f evaluated at x plus delta x, minus the y value here, which is just f of x. So that's delta y. Whereas dy, a formula for dy you can get by looking at the slope of this tangent line. So the slope of the tangent line at this point would be the derivative of the function at this point. So it's going to be f prime of x. But the slope of a tangent line can also be gotten from taking the rise over the run. And notice that when we make this much run, the tangent line rises by this much here, which is dy. So f prime of x, which is the slope of this tangent line, is equal to the rise over the run which is dy divided by dx. So f prime of x is equal to dy divided by dx, and if you multiply the dx to the other side, then you can see that dy is just f prime of x times dx. And so we have two formulas for the change in y here. One for the tangent line, the change in the y value on the tangent line, and one for the change in the y value on the function. Again, they're not necessarily the same. In fact, in certain situations, dy is approximately delta y, and we use dy to approximate the actual change in the y value on the function. Okay, so let me show you an example where we actually use this. We use these differentials. Okay, so in this example, what we're going to try to do is find a formula for the differential change in y, again labeled dy, given a differential change in x, labeled dx. And the function we're working with is y is equal to x squared. Okay, well, we already know that dy is equal to f prime of x times dx. So we just need to find the derivative of this function. Okay, well, f prime of x in this case would just be 2x. And so dy is going to be equal to 2x times dx. So now we have a formula to find differential change in y given some differential change in x. So an example of this might be, let's say you have the graph of this function, right? Y is equal to x squared would look like this. And let's say at this point x is equal to 3. You want to find the differential change in y when you move over to a point next to it like 3.1. Remember, the differential change in y is the change that occurs on the tangent line at this point. The change in the y value that occurs on this tangent line when you make this differential change in x down here. Okay, so let's find that. So the differential change down here in x would be 0.1. And then the corresponding differential change in y would be the distance between the y value at 3 and the y value at 3.1. Which is about right there. So that's our delta y. Or sorry, our dy. Okay, well, this formula will tell us what the differential change in y is, right? So x is 3, right? Remember, this is labeled as x. This point over here is x plus dx, which is 3 plus 0.1. Okay, so we just need to plug in 3 for the x here. And by the way, this just gives us the slope of this tangent line, right? This is the slope of this tangent line is equal to 6. And then we're going to run by 0.1, because dx is actually the run that occurs here. And then the dy is going to be the corresponding rise that occurs on the tangent line. Okay, so it's going to be 0.6. Okay, so that's just an example of how you would use this formula. In general, for this particular function, this formula describes the relationship between the differential change in x and the differential change in y. It's always dy is equal to 2x times dx. Okay, I hope you found this video helpful. Thank you for watching. Bye-bye.